Hello guys, I really hope you had a good weekend. This is the first time in my life that I visited another state in the United States other than New Jersey. I actually have been to Florida, but that was many years ago. Very strange. Yes, I was in such an American neighborhood that, yes, I felt very strange. I felt like a plant that was not supposed to be there. Anyhow, guys, so possibly we'll talk about impressions later. Let's get on with today's lecture. So, do you remember what is chain rule? So chain rule, that idea is that you recognize that there is one function, and that one function that you know how to differentiate has eaten another function that you know how to differentiate. Good? So the way I think of it is in terms of creatures living in the aquarium. I think of trigonometric functions as medusas, for obvious reasons, perhaps, right? You remember at the very beginning here, I discussed the type of functions that we recognize and know how to differentiate. So we have polynomials, we have radicals, we have involutions. Together, involution and polynomials, they build up rational functions. I can even differentiate that. Then I have root functions. And of course, I have functions like sine, cosine, and other trig functions, and exponentials. Those are the functions I'm familiar with and supposedly know how to differentiate. Good? I hear someone is snoring. I guess I help people sleep. So what happens here is when I take the derivative of a composition, I take the derivative of the outer function first. It's like filleting a fish, I think of it, or if you're a vegetarian, peeling off the layers of an onion. So I differentiate the outside first, like for example, derivative of tangent of root of x, it's secant root of x times the derivative of root x. Derivative of secant of 1 over x is the derivative of secant, which is secant tangent, and inside you find 1 over x, multiplied by the derivative of 1 over root x. And I try to explain why chain rule works. It's really, all of it is this idea where you play with the derivative, right? You play with the derivative, and the idea that some of you have realized is that when I see limit as x goes to a, I want to divide by f of x minus f of a and multiply by f of x minus f of a, because that will generate the derivative pattern, okay? If you develop this recognition, all the problems begin to seem very similar. I have here the geometric approach, right? Why is the chain rule working using the geometric approach? But I will not talk about it now, as we need to rush through the material. If you are interested, by all means, stay after class and we will discuss these ideas. Yes, I know some people are interested, at least a few of you, and we can discuss those ideas then. Right, so that's the linearization process. Now, let's try to solve a bunch of derivatives. So very quickly, could you please type in the comments what's the derivative to practice problem A? Come on, guys, let's solve those questions and let's do it very rapidly because we need to move on. That's very good, Ibad. Thank you. All right, so first problem, I see already 2 people answering it. Come on, guys, faster. Kirill, David, I appreciate it. So the answer is good. 100. You see, it's what? It's one polynomial that has eaten another polynomial. So it's 100 for x minus x squared multiplied by 4 minus 2x. Yes? So that's what we have. Let's now look at problem B. Would you please write in your comments what is the derivative now? Okay, Kirill. And thank you, Helen. So the derivative of this question, guys, of this problem, it's very simple. What you do is you take the derivative of sine, so that is cosine. In its belly, what do you see in its belly? You see e to the x, yes? Times the derivative of what's in the belly, which is e to the x, plus the derivative of e to the sine x is e to the sine x multiplied by cosine x. And we are done. Good. Now let's try to do the next derivative. So we have a derivative of root s squared plus 1 over s squared plus 4. Please, it's a bit ugly to write it here, but let's see if we can do it. So go ahead and type your solution. So here is that question. Oh, Miami, good morning, by the way. Or maybe at your place, it's already evening. Sumia, so think about it this way, Sumia. We have which function ate which function. So we have the root function. It has eaten what's inside. So we need to take the derivative of the outer function of the root and multiply by the derivative of the rational function inside. So here it is. Ready, guys? What's the derivative of root? The derivative of root, it's always 1 over root, 1 over 2 root. You can write it in so many different ways. But one way to do it is 1 over the square root, and here is a 2. And then what's inside is s squared plus 1 over s squared plus 4. multiplied by this derivative, right? So the derivative of what's inside of this is the inside, guys. That's the fish I find inside, and now I need to deal with it. So the derivative is I square the denominator, because it's a quotient rule now. Then I have the denominator unchanged, copied to the numerator, multiplied by the derivative of the numerator, which is by 2s, minus, and now the roles are reversed. So it will be derivative of s squared plus 4, which is 2s, multiplied by the numerator, which is s squared plus 1. I can certainly simplify it, but the question is not very, I don't want to do anything with it, just to demonstrate that I can take derivatives of it. So I am not going to bother with this question further. So on the exam, what you will do is whatever is asked, you can just you can answer that particular question. You don't have to give me further information, right? But if you do give me further information, make sure it's correct further information. Okay, now we are at D, guys. Can you take the derivative of tangent of cosine of t? With respect to t. Okay, Kirill, you're fast. You just made one mistake. You mean, first of all, it's in terms of t, but let's ignore that. You mean secant squared of cosine, not secant squared x. Yes, Lisha, good. Sumaya, great. Kelly, wonderful. Yes. So come on, guys, you can do it fast. Irvin, you forgot minus. Jonathan, Jadul, yes, great, good. Steven, you displaced because secant squared has to be eating cosine. So whatever is written here is just displaced a bit. Steven, good. All right, guys, so let's do this one. Okay, let's do this one. So the derivative of tangent is secant squared. In its belly, we definitely see a cotangent. cosine of t, I mean. Yes, and then I multiply by derivative of cosine t, which is minus sine t. I can place, I would usually put parentheses so that it's clear what's happening. So it's multiplication by this expression, or I will carry out and put the minus in front. Good. Now, there are going to be a few of them that are a bit more nasty. So you have question F. Let me write question F in the new share. I would like you guys to take the derivative of root, what was that, 1 plus x to the e to the minus 2x. Yeah, calculate the derivative of this thing, please. Okay, Helene, okay. Let's see, in a moment. All right, are you ready, guys? So here we go. The derivative is 1 over 2, because derivative of root is 1 over 2 root. Good. I could have simply written it as 1 plus x to the e to the minus 2x, but to the power of 1/2. And then I need to multiply by the derivative of the inside. And what do I have on the inside? It's a product rule, right? So the derivative of the product rule is derivative of x, so it's e minus 2x. And then plus x times the derivative of e to the minus 2x, and that involves another chain rule. So I will get altogether minus 2x e to the minus 2x, where the minus 2 dropped when I took the derivative of minus 2x. Everybody understands the calculation? Any elaboration necessary? Please let me know. Okay, but good. Okay, let's carry on with the new question, with a new question. So now we want to figure out how to take the derivative of root of x plus root of x plus root of x. I'll write it here. That can be a bit annoying. So what's the derivative of root x plus root x plus root x? You have to be very careful. Okay, Kirill? It's a bit hard to communicate such a thing through... Okay. I'll wait a little longer, guys. See if you can figure it out. You have to be simply careful, right? It's root that has eaten this function, and then we can take we can see that we have here root that has eaten this function and onwards, right? So it's just a sequence of applications of chain rule. You can maybe do something like this. That's first. Then you have second. And finally, third. So, yes. All right, guys, let's do it together. So here is what I mean when I underlined it. So the first part is the derivative of the outer root here, yes? So I can write it as 1 divided by 2 root of everything inside, of whatever is this red thing here, okay? So of x plus root x plus root x. Good. Then I multiply. Now it's the red region. So what's the derivative of the red region? It's 1 plus 1 over 2 root x plus root x. That's the red region that I dealt with. Now I am, well, you have to be careful. So it's times this, but I apply a chain rule here. So I should place it. It's very careful. Very easy to be wrong here. Now I am in the yellow region, right? So I need to differentiate what's inside. So it's x plus root x. So that would be 1 plus plus derivative of root x, it's simply 1 over 2 root x. Okay, that's the product. Okay, I just have to be very careful. I take the derivative of this expression times the derivative of what's inside. Now what's inside, it's 1 plus the derivative of this root, which is 1 over 2 root x plus root x. And then I need to take this function and take its derivative, which is what I see over here. So then you might wonder if this question is much more difficult, right? It's so we have derivative of root of x plus root x plus root x always or forever like this. What's the derivative of this function? Can you figure it out? That's a good idea. Why not? But right, so you are thinking very well, right? You can figure out it's a fractal, so we could possibly create something nicer here. All right, guys, here is the hint. F of x we can think of it, it equals to root of x, and because it's infinite, everything we see thereafter is identical. Okay, so what we can do is we can actually figure out implicitly what the derivative is. We haven't talked about implicit differentiation, but we can actually solve it. Look at it. So if this is y, so we have that y equals to root of x plus y. So that means that y squared minus y minus x is equal to 0, which means that y equals to the square root. So sorry, let me actually write it here. So y is equal to 1 plus the square root of 1 minus 4 times 1 times minus x. So it's 1 plus x. 1, yeah, so there's a 4 here, right? Divided by 2, so it's not so difficult to differentiate this function. You with me, guys? So what I did is, you know the quadratic formula. So you have is y equals to minus b plus or minus root b squared minus 4ac divided by 2a. In this case, a is the coefficient next to a, which next to y squared, which is 1. The coefficient b is minus 1, and the coefficient c is minus x. So that's how I got this expression. Now, the derivative dy dx is now very simple to obtain. It's simply 1 over, I take the derivative of this expression, right? It's the same as taking the derivative of 1/2 of root of 1 plus 4x. So it's really, here we have 4 root 1 plus 4x multiplied by 4, or 1 over root 1 plus 4x. Are you with me? All right, guys, did you understand the idea? Let's move on. Okay, next lecture. Now we need to talk about logarithms, guys. Do you remember logarithms? So here is just a brief review of what is exponential supposed to be doing. So we have that if I multiply a number of times by itself, then let's say a times a times a can be written as a cubed, or 5 times 5 times 5, it's 5 cubed. In general, if I multiply a number by itself n times, it's a to the n. And this is a convenient way to keep track of multiplication. And then we observe that if I have a to the power of n times a to the power of m, that would be a to the power of n plus m. Yes, so for example, a to the 3 times a to the 4, it's simply I realize I multiply a by itself 3 plus 4 times, or 7 times, right? It's also easy to see that a to the n divided by a to the m, it's simply a to the n minus m, right? If the above power is bigger, what happens here? Why do we have numerator power minus denominator power? Is because of the cancellations. So I cross things out and I'm left with a in this case. And of course, if it's in reverse, if it's a to the 3 divided by a to the 4, I will only have a surviving on the bottom. So that's why a to the power of minus 1 equals to 1 over a. And in general, a to the minus k equals to 1 over a to the k. Good? And that tells us, as you remember, that a to the 0 is equal to 1, because that means when I had 0 as the power, it means I had division and nothing survived. Like a to the 0 is a to the 1 minus 1, which is a over a, which is 1. Before I move on, please confirm that this is understood. Please write yes. We did it a few times. So here is a quick comprehension check, guys. I appreciate it. Thank you. Now, quick comprehension check. What is 0 to the power of 0 and why that's the case? Are you there, guys? So 0 to the power of 0. What is that? Okay, Irvin says 1. 0 to the power of 0. What is that, guys? Zakia now says 1. 2 people say 1. Steven says 0. Kelly says 0. And David says everything to the power powered by 0 is 1, question mark. Is 1 or undefined? 1, 1, 1. You said you understood it, guys. So more solutions. But Erwin, 0 divided by 0. What is 0 divided by 0? Well, you can be caught in metaphysical debris. So again, guys, you see when I say a to the power of 0 and I say it's equal to 1, I am talking about this situation, right? I'm saying, well, I can think of how would I obtain such a situation? If I have 0 to the power of 1 minus 1, that will give me 0 to the 0. But that means 0 divided by 0. And what will that be? 0 divided by 0, what could that be? Well, again, I think you forget some important ideas, guys. What is 0 times anything? Any real number. That is 0. Do you know why that is 0? 0 times anything, why is it 0? Because I can say that this is the same thing as 0 plus 0 times anything. And so I can distribute the anything, so it's 0 times anything plus 0 times anything equals to what it used to be originally, 0 times anything. And then I can cancel out this and that, and I see that the result is simply 0 times anything is 0. That's very important. It's very important to understand why 0 multiplied by any real number is 0. Now, what's the problem of dividing by 0? So when I say, for example, something like, 3 divided by 5, I mean 3 multiplied by 1 over 5. What is 1 over 5 means that if I were to multiply this number by, if I were to multiply this number by 5, I will get 1. Okay. So in particular, why can I divide by 5? Because you can say that 1 over 5 is a meaningful quantity, because 5 times 1 over 5 is 1. 1 over 5 is the number that through multiplication by something will give you 1. through multiplication by 5, right? It means multiply me by 5 and you will get 1, okay? Now, what about 1 over 0? This is saying multiply me by 0 and get 1. But if I multiply this by 0, if I do indeed get 1, that would also mean from the previous theorem that anything times 0 is 0, that 0 equals to 1. That's a contradiction. Do you understand, guys, how the contradiction works? 1 divided by 0 means the expression is saying multiply me by 0 and get 1. But if you multiply me by 0, you get 0 based on that previous result. So I cannot make 1 over 0 defined. Do you understand the explanation, guys? Confirm if you do. That's just a very quick, short explanation for why you might think that you cannot divide by 0. Yes, come on, guys. You can tell me, of course, if something is not understood. I will try to do that again. So it's not coincidental that you cannot divide by 0. So that means that, yeah, so it was undefined. Because of that, we say that we cannot define division by 0. So it's undefined. Because it would be, because 0 to the 0, it's like 0 divided by 0. Yes, and if you study it a bit deeper, this becomes more meaningful to you, right? So I do not know if you would appreciate this information, is that in complex analysis, you can divide by 0. In complex analysis, 1 over 0 is infinity, because infinity is actually a meaningful quantity, okay? So when I say something cannot be done, you have to understand what do I mean by that? What exactly am I trying to say when I say it cannot be defined, it cannot be done, okay? So you have to really, so when people tell you cannot divide by 0, you have to understand what do they mean. It's just how do you interpret those symbols. 1 over 0 is interpreted in this situation as a number that when you multiply by 0 should give you 1, but anything multiplied by 0 by the distributive law will give you 0. So you have 0 equal to 1, and that's the contradiction. Good. So then we can see the following. We can see this property 4 is that if I take a to some power n and then I raise it to yet another power m, I get a to the n times m. And for instance, you can see that a squared cubed is going to be the same as a squared multiplied by a squared multiplied by a squared, right? Because whatever is in the parentheses cubed, it means you just copy it 3 times and write product between them. So altogether, this is also a times a times a times a. It's a to the 2 times 3. So you can see that you can multiply those powers. And in general, how do you see a to the n to the times m? You can put it in a matrix, right? So I have, matrix is this. You see, we have here a to the n, 1 copy. Then we have another copy. Then we have another copy, and we multiply them all. How many multiplication do we carry out? This is a to the n, this is another a to the n, this is another a to the n. Altogether, they're going to be how many copies of a? M multiplied by n. Do you see? So why a to the n to the power of m is going to be a to the m multiplied by n. Are you with me, guys? All right. Now, another thing that we need is that the nth root of a is represented by a to the 1 over n. Why do we have that representation? Well, think about it, right? If I want to create a representation, so I want to say that there is some number x that creates the nth root. That means that, what's the nth root? It means multiply this number by itself n times. It's the nth root multiplied by n times, you should get a. Yes, and if you wish this law to continue to hold, that x times that it will be x times y, even when x and y are not necessarily both integers, then we want x times y to equal to 1, where y is n, right? So I want this law to still hold even when x is not an integer. So that is x times n equals to 1, which means x equals to 1 over n. Do you understand? You can continue defining the operations so that those the algebra I observed with integers continues to hold for other numbers. And I will not bother you with that, but I'll spare you the torture right now. Is that but you can see that a to the power of m divided by n I can define as a to the 1 over n raised to the power of m. And that is non-trivial to verify, because look at it, guys. What does this mean? So for instance, I might say that a to the 1 over n as a fraction, it equals to k divided by kn. But the meaning of k divided by kn, you think right away I can cancel the k. The meaning is different. If that's what I mean is the meaning, then I would have to verify that that taking the kn root and then multiplying the kf root by itself k times will give you the same result as if I just take the nth root of the number. So let me illustrate with this example. So we have the cube root of 5, right? You can see that 1/3 is the same as 2/6, but here on the left I am asked to carry out an entirely different operation. Right here I am asked to find the third root of 5. What am I asked to do here? I am asked to first find the 6th root. You understand? I'm not writing it, but this means find the 6th root of 5, which is different than finding the third root of 5, and then multiply the result by itself twice. Will I get the same value? Do you understand my question, guys? Do you understand that why I'm saying even that is not trivial? You would just, you never thought of it, so you'll probably simplify 2 and 6. But the meaning of this expression, based on what I wrote over here, is different than the meaning of that expression. I do entirely different operations. Here, I take the cube root of 5 and I'm done. Here, no mention of cube roots. I take the 6th root of 5 and then I multiply the result by itself twice. So I carry an entirely different operation. And as it happens, the result will be the same. Do you understand the difficulty that I'm trying to point out? Please write to me if you see it. I want to know. So Mayamiko and anyone else here, you see, when you do real analysis, when you talk about calculus, you actually have to be very careful and describe the real numbers. You have to describe what they are very precisely, because there are going to be significant consequences if you select a different number system. So for instance, what is the cube root of 1? How would you answer this question? The cube root of 1. 1 to the 1/3 is the cube root of 1, yes? What would you say? So Kirill says 1, and what about the rest of you? Okay, Irvin says 1. Okay, and now that a few people said 1, the others are confident and they are writing 1. So in the real number line, you are certainly correct. There is only one cube root of 1, because only 1 times 1 times 1 will give you 1. But if you go to complex analysis, to a different number structure, you will have actually 3 solutions. So you have the solution 1, you have the solution -1/2 plus root 3 over 2i, and -1/2 minus root 3 over 2i. So you see, because complex numbers are a different structure. If you take the 5th root of 1, you will have 5 solutions. Good? So you don't have to worry about it, but I can try to explain it. So any truly good course on calculus begins with a discussion of what real numbers are and how they are different from other number systems and what sort of calculus will you have with other number systems? All right. All this, Mayamiko, yes, there are definitely a set of numbers. So, guys, by the way, out of curiosity, how many of you know what complex numbers are? What are they doing, complex numbers? Well, let me tell you what they are for, right? If you want to describe a machine, you see a number, I think of it as a state of a machine. So what complex numbers are doing? Imagine that you take a big infinite plane, like a huge infinite. Yes, that's a complex number, Zainab. If you take an infinite plane, just imagine a white paper, right? And you imagine you have a drawing on it. So what complex numbers are capable of expressing? They are capable of expressing stretching something out, rotating it, and moving it and shifting it. So complex numbers are states of geometry. It's a system capable of describing geometric transformations in the plane. So for example, when you compare one triangle to another, that's complex numbers. I do not know if I have the lectures note. I mean, if I have for complex, do I have the book posted here, or I deleted it? Let me see. Here you can find lots of interesting things. Well, yeah, I mean, I might not have it posted here, but it's okay. I can show you. If you're interested, we can talk about it. We can talk about it more. Let's guys. Has anyone, by the way, tried to read the quantum physics book that I suggested? Anyone try to look through it? Not interested? Well, that's too bad. Well, anyhow, guys, so here we have a bunch of equations, right? And please, I wonder what you would have said. Okay, so let's talk about logarithms, right? So the question is really, how do I solve equation? How do I find a representation for x? For a, it's trivial. If I put x equal to 2, it works. If I put x equal to 3, it works. What do I do for c? What would you select x to equal to give the value 1? Yes, 0. So by the way, Mayamiko, I'm not sure if I finished answering your question. I would say this, right? Is that you see, if complex numbers are discussing the plane, then of course you have other geometry in higher dimensions. So that would necessitate other number structures to describe. And so in principle, there could be infinitely many. Complex numbers contain real numbers as a subsystem. So complex numbers are more complicated. It's a more sophisticated machinery, but you can do it. You can create more sophisticated machinery beyond complex numbers. So what else? So we know that 2 to the 0 is 1. So we can solve a through c. We can more or less easily solve. What about d through f? What would you have led? So I want it to be 1/2. What would you make x equal to? So d through f, what would x equal to? So this -1, this the next one, e is -2, and f is -3. Do you agree? -3 means that 2 multiplied by itself 3 times survived in the denominator. That's why we get 1/8. And then we have g through I. What would you write for g through I, guys? Quickly, let me know, please. Yes, thank you, Kirill. And the rest of you guys, come on, you can do it. What do you write for x to have this represented? Thank you, bud. Yeah, no trouble, right? So -1/7. Thank you. So again, right? I hope you understand why 1/2 represents root, guys. Do you understand why 1/2 represents root? Why is it not another expression? Why did we pick 1/2 to represent the square root? I explained it in general, right? But do you understand why? When I have this situation, when I have 1/2 multiplied by, let's see if I have, sorry, 2 to the 1/2. If I square it, I want to get 2. But if I square it, it's according to that rule that I hope that I want to maintain to be true. It's 1/2 times 2, so it would be 2 to the 1, which is 2. So that's why 1/2 is this number, because in general, if I select anything other than 1/2, it will not be true that this power multiplied by this power gives me 2. Yes, but even more so, it's notation to continue that analogy, right? That with integers, I verify that a to the n to the power of m is a times to the power of n times m. I want this analogy to still hold, right? And so here those are all what I can consider them guesses, yes. But how about this equation, guys? 2 to the power of x equals to -4. What would you say for this equation? What would x be if 2 to the x equals to -4? So guys, what's going on with you? 2 to the x equals to -4. What goes in your head? Does not exist. Yes, yes, yes. So it does not exist in what sense? It does not exist in real numbers. Yes. You cannot use real numbers because obviously 2 to the 0 doesn't work. But if x is bigger than 0, 2 to the x will be some multiplication of 2, or it will be positive. If x is negative, it will still be positive, right? So 2 to any power will be positive because it's either 1/2 to a positive power or 2 to the positive power, and I will never get a negative number. So there is no real number that solves this equation. Now we get to the next complexity. What about 2 to the x equal to 5? How would I solve this question? 2 to the x equal 5. Yes, Kirill. But even if you say so, what does the answer mean? You see, guys, what is 2 to the x equal to 5? How would you find this x? What would you do? Well, that's great, Erwin. That's similar. But what does it mean? And okay, let me just, because our time is running short. Let me tell you that 2 to the x, the way you say, the way you solve it, you say x equal to log base 2 of 5. And if you actually spend a little time thinking about what it means, you might protest, but you haven't said anything. Because what is this saying? What is log base 2 of 5? This says, place me over 2 and you get 5. You understand? This just means place me over 2 and get 5. It's like Alice in Wonderland vial with this tag, and the tag says drink from me and you will be shrunk. Do you understand what I'm saying? Place, in general, when I want to know the solution to a to the power of x equal to b, I can say x is equal to log base a of b, which means some x is some number that is placed over a and gives you b, provided the number exists. Okay, this is the analogy. It's just a tag, right? As many things are just tags. Just if you think about it, guys, when I ask you what is root of 7, right? What does it mean? It means a number that this means square me and get 7. That's what it means. It's pretty amazing that having named something, you achieve your first victory over that something. You see, I am not particularly religious, but I found it interesting that in the Bible, in Genesis, the animals in the Garden of Eden are paraded in front of man, and he names those animals. Do you understand that already in ancient times you believed that if you can name something, then you already have control over it? The scariest things are the things that cannot be named because they are beyond your power. Do you understand that? In mathematics, there is a precise sense why that works. As soon as you name something, you can figure out how to control it. I wonder if you remember my name. And with that, today's lecture is over. Goodbye, unless you want to stay for office hours and ask me something. Take care. Adieu, goodbye, auf Wiedersehen. Actually, not auf Wiedersehen because you don't show your faces. Auf Wiederhören if you speak. Or auf Wiederschreiben if you actually decide to write something to me. Good day. Goodbye.